Now we move on to colloids. So as an introduction, we know that when we dissolve salt in water, the effect is that we have a homogeneous solution, a homogeneous mixture, right? So you don't see any salt particles in your liquid, so it's homogeneous. On the other hand, if you put sand in water, you stir it, and after some time, you observe that the sand will settle down. So we can distinctly see the sand particles and the water above it. So we have a heterogeneous mixture. But how about milk? So it's sort of homogeneous, but actually it's neither a solution nor a suspension, which is a heterogeneous mixture. So milk is actually a colloid. So how do we distinguish between these three types of mixture? So the distinction is in the size of the particles dissolved in your solvent. So the solution has the smallest particle size. So solutes are very, very small in solution. That is why we have a homogeneous mixture. So we don't see the solute particles with our naked eye. On the other hand, suspension has the largest particle. That's why they remain suspended in the liquid. And hence we have a heterogeneous mixture. So the colloid is somewhere in between your solution and your suspension. So the colloid has a sort of solute, whose size is larger than the solute of a solution and um, less than the size of a particle we find in a suspension. So in colloids, we have the dispersed phase. So the dispersed phase is the counterpart of solute, and the dispersing medium is the counterpart of the solvent. So aside from milk, what other colloids do we have? So have you ever woken up in your room and then you see the ray of sunlight entering your room through the window, and sometimes you also see dust particles floating around? So this is actually an example of a colloid. Um, Also, when you see cars in the night, you see the headlight, right? You see rays of light coming from the headlight of another car, and also sometimes you see dust particles floating. So it's the same. So actually, these examples of colloids display a property unique to colloids. The property is called the Tyndall effect. So, what is this Tyndall effect? So actually, but the size of the particles in a colloid is enough for it to reflect a light wave. Okay? If the particle is too small, then it cannot reflect a light wave. The same goes for the big particles that you see in suspensions. So again, in colloids, the dispersed phase has size enough to reflect light. That's why colloids display Tyndall effect. So here are some types of colloids. So you can actually have combinations of all the phases. We have liquid and gas. So this is aerosol, mist. Okay, we have solid gas. This is also called aerosol. So we have smoke. So the colloid that can reflect light in your room, the reason why you can see the ray of sunlight is actually an aerosol, specifically a solid gas type of colloid. We have gas liquid, so it's named foam. An example will be whipped cream. And we have liquid liquid, it's called an emulsion, and an example is mayonnaise. We have solid liquid, so it's called sol. An example is milk of magnesia. We have gas in solid, so it's also a foam. An example would be plastic foams, like styrofoam. We have liquid solid, liquid in solid, so it's a gel. An example would be jelly. And then we have solid solid, so it's a solid sol. An example would be some certain alloys. So it's a mixture of two metals, for example. Now, in addition to the phases of the dispersed phase and dispersing medium, we can also classify your colloids whether they are stable in water or not. So if they are stable in water, so they are water loving, we call them hydrophilic colloids. So an example of hydrophilic colloid will be proteins. So proteins are very large molecules and most of them have this globe-like shape. So they are very round. And interestingly, on the surface of your proteins, you have certain functional groups. So we call them functional groups, and some of them have charges like this NH3 plus and this C double bond OO minus. So since they are charged, their interaction with water is very favorable because we know that water is polar. So these ions can form ion dipole interactions with water. So proteins in water is a very stable mixture or colloid. On the other hand, we have what we call hydrophobic colloids. So they are water-fearing colloids. An example, classical example would be oil in water. So we know that oil never mixes with water. So if we have this oil in water mixture and then you try to shake it, so you will see very, very, very small droplets of oil dispersed in water. That is your colloid. So if you see two layers, so in your container, if you see two layers, so we have oil here and then water at the bottom, this is not a colloid, okay? Because one of them must be dispersed in the other. So you need to shake this so that you have small oil droplets dispersed in the water. That is your colloid. But since it is not stable, so because it's hydrophobic, it's not stable, if you let it stand for some time, you will see that the oil will separate from the water and then it goes back to the original state, wherein you have two layers. So there are ways for these hydrophobic colloids to become more stable. Okay, so one way to stabilize hydrophobic colloids is by the use of salts. So you know that salts produce ions in water. So these ions, they attach to the surface of a colloidal particle, and since they are charged, they can favorably interact with water. At the same time, if the same charges attach to the surface of two colloidal particles, then there will be repulsion between the particles. So it prevents them from coagulating with each other. So that stabilizes the dispersion of the colloidal particles, right? And then another way of stabilizing your hydrophobic colloids is by the use of an emulsifying agent. So an emulsifying agent has two important properties. One is it has a hydrophobic tail. So it has this long stretch of hydrophobic atoms or groups. So this hydrophobic tail doesn't interact with water, but it can interact with your oil, for example. Then the next important property of an emulsifying agent is that it should have a hydrophilic head. So this hydrophilic head can interact with water. So a classical example is sodium stearate. So if you look at the labels of your shampoos or conditioners or liquid soaps, you will see either stearate or palmitate, laureate, oleate, etc. Those are actually emulsifying agents. So how does an emulsifying agent work? So for example, we have here grease, which is mostly composed of oil. Okay, let's say this is our skin. So we have grease. Then we put some emulsifying agent from your soap. So you put soap. The emulsifying agent has a hydrophobic tail. So the hydrophobic tails will interact with your grease. And then, of course, the hydrophilic heads will stick out from the grease because they don't form favorable interactions with the grease. Now, if you put water, so you wash your hands with water, what happens is that the hydrophilic heads will interact with water, and that helps in removing the grease. And so that's it for the first chapter of our course, Solutions. So the next chapter will be on thermodynamics, so please watch out for the videos on thermodynamics. And I hope this installation on colloids will help you in your homework, the one with the mayonnaise. See you when I see you.